Hi everyone! In this video we're going to start discussing the reactivity of amines. So the first reaction we can perform is called acylation. So let's say that we have para-hydroxyaniline. So we've got our alcohol group opposite the amino group there. And we're just going to add an acyl chloride, and the acyl group is going to bond with nitrogen. So we end up forming an amide over there, although the nitrogen is still attached to the benzene ring. So we just added this acyl group onto nitrogen. And this is actually referred to as Tylenol. So this is one way that you could make Tylenol. Another way, instead of using that acyl chloride, you could also use an anhydride. And one advantage of using an anhydride is that they are more selective, so they won't react with anything else on the ring, whereas an acyl chloride could potentially react with other functional groups. So we'll just write anhydrides are more selective. So, depending on what's on your benzene ring, that could be advantageous. All right, so let's talk about why acylation is really useful. So one example, let's say that we have aniline. And we want to add bromine onto the ring. Now, if we just add bromine with our catalyst, iron tribromide, where do you think bromine would add on the ring? Or another question to ask is, are amino groups electron donating or electron withdrawing? So will they be ortho-para-directors or meta-directors? So amino groups are electron donating, so they will activate the ring, which means they are ortho-para-directors. So we could potentially add bromine to either the ortho or para positions. And in fact, what we might end up with here, or what we probably would end up with, is a mixture of products where we have either mono-substituted products, di-substituted products, or tri-substituted products with the bromine adding in. So we could have mono, di, or tri-brominated products. Okay, and maybe in some instances we would want that, but what if we just want bromine to add once? Well, it is really difficult to add just one equivalent of bromine, so another option is to use acylation. So we'll add an acyl chloride, and that will add to our nitrogen. Oh, chlorine will not be there. So now if we add bromine, where do you think bromine is going to add? Well, looking at the group that we now have at the top of the ring, that is a moderate activator. So it's no longer a strong activator. And that's because of that carbonyl group. Because if we just draw in our lone pair there, we could either donate electrons into the ring or away from the ring. So we're only going to add bromine once because the ring is no longer very activated, it's just slightly activated. Now, do you think that that one bromine will add to the ortho or para position? Well, if we look at our acyl group there, it's kind of made that nitrogen a little bulky, right? So we kind of have a bulkier group on top. And bromine is a fairly large atom, so it's probably going to add to the para position. Now, at the very end, we probably want to get rid of the acyl group so that we can go back to our amino group. So to do that, you would just add some acid and heat. And that will give us back our amino group. Now, another reason that acylation is really useful is, let's say again we have aniline. And we want to add or perform Friedel-Crafts alkylation. So we want to add a methyl group. Unfortunately, this is just going to give us a big old mess. So we'll see over-alkylation of the ring. Additionally, that amino group could perform a substitution reaction with our methyl group there. So we could even add a methyl group to the nitrogen. Additionally, the amino group could react with aluminum trichloride, the catalyst. So it could form a Lewis acid-base adduct. With aluminum trichloride. So there's a lot going on here, and we could end up with a whole mixture, a bunch of different mixtures of things. So to avoid that, we can just acylate the amino group. Now you might be wondering, I think I did a reaction like this in the past where I used Friedel-Crafts alkylation, and that's okay. We didn't know that it would create a big old mess, but now we do. So what we'll do is, to avoid a big old mess, we will acylate our nitrogen. We'll add in our same Friedel-Crafts alkylation reagents. And then, similar to the reaction we saw on the last slide, the methyl group will add to the para position. And again, we can just use acid and heat to remove the acyl group at the end. All right. So again, this is another useful part of acylation. We can avoid some of these messy products. So let's talk about another type of reaction that we can perform with amines, and that is Hoffman elimination. So remember way back when we were talking about substitution and elimination, we said that there was Hoffman elimination and Zaitsev elimination. Now, Hoffman elimination referred to forming a less substituted alkene. So let's just write that down. Okay. So let's say that we have an alcohol. And we're going to compare that to the same type of molecule, but we have an amino group instead. And we're trying to form, oh, there we go, this product here, where the double bond is between a less substituted carbon. So it's on the very end of the molecule. Now, remember way back we said that alcohols aren't very good leaving groups, so we probably need to convert it to a better leaving group first. So one way that we did that was by adding a tosyl group. And then we used a base to take a proton. Now, would we want to take the proton from the more substituted carbon or the less substituted carbon here? The less substituted carbon. So would we want a small base or a large base? A large base, because then we'll form the less substituted alkene. Because the bigger the base, the harder it is for it to take a proton in the middle of the molecule. So we could use something like potassium tert butoxide or DBN or DBU. Or you could also just use an acid like sulfuric acid, which would be catalytic, and then also add in heat. So either way. Similarly, if you have an amine, you have to first convert the amine into a better leaving group. So what we're going to do is over-alkylate the amine. And we'll do that by adding excess methyl iodide. And then we'll follow that with a base to perform elimination. So let's draw the mechanism for this. So we'll start with our amine. And we're going to first add excess methyl iodide. And this is going to be an SN2 reaction. So the nitrogen is going to attack that methyl group, and we're going to over-alkylate the amines. So we'll have 3 methyl groups attached once everything is said and done. And that is actually a very good leaving group. So here we'll just kind of circle that and say good leaving group. So there are a couple of different ways we could go here. So for instance, we could use a couple of different types of bases. The first one we're more familiar with, so we could just use potassium tert butoxide, and that's going to take a proton from our methyl group on the end of the molecule, and then we'll form a double bond, and our leaving group will leave. So then we get our desired product plus our nitrogen bonded to 3 methyl groups. And then we'll also end up with the tert-butyl alcohol. Another option is to use silver 1 oxide, which we have not seen before. So this is Ag2O, silver 1 oxide. So in this reaction, we end up replacing the iodide ion up above with a, or we kind of remove that iodide ion using the silver. And then we replace it with a hydroxide. So the silver iodide kind of precipitates out of solution. And then our alcohol, or sorry, our hydroxide, not alcohol, that will come in and take a proton, and we end up doing the same exact mechanism as above. We just have a slightly different base there. Okay, so we've end up forming the same products at the end, except instead of the butoxide turning into an alcohol, we would form water as our other byproduct. So one reason that we would use the silver 1 oxide is silver 1 oxide is gentle. So for instance, it won't do any SN2 or acid-base chemistry, and it kind of helps remove those iodide ions as well. Now, regardless of which type of base you use, we do have to think about regiochemistry when we're forming these alkenes. Oh, it won't let me go to the next slide. Let's see. There we go. So, for instance, let's say that we have that same amine, but this time we're showing the stereochemistry. So we'll draw the amine as a wedge here. And we're going to, again, over-alkylate our amine. Now we're going to add that silver 1 oxide, and that's going to again replace our iodide ion there with a hydroxide ion, which will act as our base for elimination. So let's just draw that real quick. Now, when we're trying to decide which side we'll take a proton from, so are we going to take the protons on the more substituted carbon, or will we take a proton from the less substituted carbon? We want to think about the regiochemistry. So we want to think about which side's better. So what we can do is draw the Newman projections. I know Newman projections are everyone's favorite. So if we were to look down that blue bond there that I drew, we would potentially see that it's unfavorable. If we look down this green bond here, we would actually see that it's more favorable, and this is why we end up forming the less substituted alkene. So let's just draw the Newman projections for both of these scenarios. All right, so for the blue bond, we would see a methyl group and 2 hydrogens on the front carbon. On the back carbon, we would see our nitrogen bonded to 3 methyl groups, another methyl group, and a hydrogen. Now, remember, in order for elimination to occur, there has to be a hydrogen that is anticoplanar to our leaving group. So our leaving group is this nitrogen bonded to 3 methyl groups, and anticoplanar to that is this hydrogen here. However, notice that we have some gauche interactions there. And here I'll just write a note that that is our anticoplanar hydrogen. Okay, but if we look down the green bond, our situation is a little bit different. So looking down the green bond, the front carbon has 3 hydrogens because it's a methyl group. And then in the back, we have our nitrogen bonded to 3 methyl groups. That's our leaving group. And we have a hydrogen and an ethyl group. So notice that our leaving group no longer has any gauche interactions with the ethyl group, for instance, or a methyl group or anything. So our anticoplanar hydrogen is easier to take because this is a more stable interaction, or a more stable situation, I should say. So this is why we form the Hoffman elimination product, because when we draw these Newman projections, we can see that taking a hydrogen from the less substituted carbon is the more favorable scenario energetically, because if we try to take a hydrogen from the more substituted carbon, unfortunately, there's really unstable interactions going on, and it would just be really difficult. So the barrier there is just too high. Okay, so the main message here is that if you do want to form the Hoffman product here, which you can, you first have to convert your amine into a better leaving group. So we're going to over-alkylate it using an SN2 reaction. And then we just want to use some sort of either bulky base like potassium tert-butoxide to perform elimination, or we could use that silver 1 oxide. Either one works. Now, remember that you are going to form that less substituted alkene just due to the stability of the less substituted carbon protons. All right, so in the next lecture, we're going to talk a little bit about diazonium salts, which we saw in lab. We made some azo dyes using diazonium salts. So I will see you then.